continuing on with the wonderful world of water, normally when a liquid sample freezes to become a solid, the liquid particles slow down, they come closer together when they transition to the solid state, which means the volume decreases, the density is then going to change. The mass is still the same, but the density is going to increase, and so that solid would sink. Water, of course, being different, when water gets to about 4 degrees Celsius, then we start to see the molecules spreading out into that honeycomb-like pattern. And when that happens, water's volume actually increases. And so the density decreases, and we end up having the floating of solid ice in liquid water. That video we saw the other day, the world of chemistry, again, when water freezes, because of the gabillions of different arrangements that could happen, we end up having these very pretty snowflakes, and no snowflake is the same. Is that true? I don't know. I never looked at them all. But more than likely, there's such a uh, incredible number of different ways and different patterns that we've seen in snowflakes, it would be very hard pressed to say that they are repeated. But again, we end up having the fact that ice does float on liquid water, and the density of ice is about 0.917, and this is fresh water ice, and the density of regular water is 1.0. So in theory, we have about 8.3% of an ice cube that is floating above the surface, and the rest is below. Again, I got that because the density of water is 1.00. The density of ice, 0.917. That's a difference of 0.083 times 100 is 8.3%. Now, a glacier typically is fresh water, and then salt water has a density of 1.025. And so when a piece of a glacier breaks off and is floating as an iceberg, slightly different math, but essentially you might have heard before, about 90%, 89.5% of the iceberg is below the surface, and about 10% of an iceberg is above. Again, that's because of salt water in the ocean instead of regular water. And then because water doesn't sink when it floats, we don't have completely solid, frozen lakes, rivers, ponds, so life can still survive underneath that. It's insulated by that layer of ice on the top, and we have fish and other creatures that survive in extreme conditions under that ice until the spring thaw. All right. So water is known as the universal solvent because it can dissolve so much stuff, and that is very beneficial, but we also see problems with pollution and industrial waste because of the fact that water is used in the industrial process, and then these contaminants get in the supply and stay there until we get to the purification process. But it does dissolve so much stuff, it's called the universal solvent. How does water dissolve stuff? And what do we get when we do have stuff dissolved in water? Well, when we have a solute, and typically we're talking about a solid solute, and it dissolves into a solvent like water, then we end up having a solution. If water is the solvent, then it is what we call an aqueous solution. And so that's what our whole next unit is going to be about, these aqueous solutions using water as the solvent. Other chemicals can be used as the solvent, but for us right now at this level, predominantly talking about water being the solvent. Again, we have this phrase, like dissolves like. So water, being polar with its partially positive and partially negative, it can dissolve other polar substances as well as ionic. So those types of solutes will easily dissolve, and I'll show you how here in a minute. Nonpolar solutes cannot dissolve in water. However, nonpolar solvents will dissolve nonpolar solutes. So here we see a chunk of iodine, and it just sits at the bottom of a water sample. But in carbon tetrachloride, which is nonpolar, it readily dissolves, and you see that purplish color that is associated with iodine. And this is happening because using repulsive forces that are breaking the solute apart. As opposed with water, essentially the solute gets attacked and ripped apart, if you will, because water uses its charged parts and is attracted to the oppositely charged parts and pulls it apart. So, for example, here, dissolving sodium chloride. And so the partially positive sides of water, where the hydrogens are, surround and pull apart the chloride ions that are negative, whereas the partially negative parts of water, the oxygen parts, surround the sodium ions. So we'll check out a little video here showing this in motion, if you will.
Sodium chloride crystals are held together by attractive forces between the positively charged sodium and negatively charged chloride ions. When a crystal of sodium chloride is placed into water, the hydrogen ends of polar water molecules attract the negatively charged chloride ions and gradually surround them. Likewise, the oxygen ends of water molecules are attracted to and surround the positively charged sodium ions. The hydrated ions drift away into the solution, allowing new water molecules to surround newly exposed ions. Gradually, the entire crystal dissociates into solution.
We heard a couple words in that video that we'll be using. One, he said, the hydrated ions. So again, if an ion or particle is totally surrounded by the solvent, we say that it's experienced solvation. Not salvation, solvation. Now when water is the solvent, again, which we typically talk about, we say that those particles are hydrated because they're completely surrounded by water molecules. Another word he used in that video was dissociated, and we'll be talking about dissociation factors of substances when we talk about colligative properties of solutions. I know, exciting stuff coming your way. Now, once we have a polar or ionic solute dissolved into water, then we end up having what we can experience, as we saw earlier in the year, electrolytes. An electrolyte will conduct an electric current when it's either molten or dissolved in water. And so we can have strong electrolytes because they're very dissociated, very dissolved. There's tons of ions in the water, so we get a strong lighted response. And we can have weak electrolytes, which means that we have dimly lit bulbs or less electric current being conducted because there's not as many particles dissociated into the water. We can also have non-electrolytes, which means that no electric current will be conducted if a substance dissolves in water and is nonpolar, like a molecular compound like sugar or other stuff we'll see here. And there's a bunch listed in your packet. All right. If it's not listed in the packet, remember you can check is something polar, nonpolar, or ionic by checking the electronegativity difference with the bonds. And it gets more complex, of course, with the molecular geometry that we looked at and whether or not the dipoles cancel. But for right now, we're just going to be looking at some simple substances and single bonds that you can easily figure out if it's polar, nonpolar, or ionic. So here's the little sample of substances I wanted to find out. Are they strong electrolytes, weak electrolytes, or non-electrolytes? Well, let's find the strong electrolytes first. And the ones that I have as strong, hydrochloric acid is a strong electrolyte. Potassium bromide, a metallic halide, because bromine is a halogen. That's strong. Nitric acid, another strong acid. is a strong electrolyte. Lithium fluoride, another metallic halide, is a strong electrolyte. Sodium iodide, another strong uh, uh, metal halide, sorry. Magnesium hydroxide was listed in your packet, and those are the ones that I have as strong electrolytes. Again, like potassium bromide, sodium iodide, I know they weren't in your packet, but if you look at that electronegativity chart, okay, sodium 0.9, iodine 2.7, that's a difference of 1.8. It's polar, so we definitely know it will dissolve in water and will be a good electrolyte. So that's how you can use that chart. Weak electrolytes, the ones that I found being weak electrolytes, I believe citric acid was one of the weak electrolytes, so was ammonia, NH3, as well as lead 2 chloride. And those are the ones I had as weak electrolytes. The rest, non-electrolytes, fructose and sugars, butane, an organic compound, oil and water don't mix, okay, ethanol, that is found like in alcoholic beverages, methane, another organic compound, and carbon tetrachloride. We saw that earlier, how it was able to dissolve the iodine. So there's our answers. Again, the yellow are the strong electrolytes, the blue are the weak electrolytes, and the green are the non-electrolytes. So the last topic here is looking at writing an equation that shows how an ionic compound dissolves in water, and simply, again, that word that was used, that solid compound dissociates into its ions. So sodium chloride as a solid breaks into the sodium plus 1 ion and the chloride minus 1 ion, and we put that AQ there, aqueous, meaning dissolved in water. A little more complex when you have more complex compounds like aluminum sulfate. Again, it's a solid, and so again, we really want to pay attention to our little symbols. They start as solids, then they turn into aqueous because they're dissolved in water. But here we see dissociates into aluminum ions, which are plus 3, but as the formula shows, there's 2 of them that are going to come out. And then sulfate, which are minus 2 ions, there's 3 of those that are going to come out. So this aluminum sulfate is going to dissociate into 5 different ions. All right, that wraps up our trek through water and beginning of dabbling into solution chemistry. So hope that helps. Good luck on your online test.